Welcome to our video presentation on 3D reconstruction and synthetic data generation for artificial intelligence model training. In modern defense and aerospace applications, developing robust AI models depends on access to vast amounts of labeled data. However, collecting and labeling real-world images in these domains is often costly, time-consuming, and sometimes even impossible due to security constraints and lack of access or rarity of the specific objects or vehicles. Our research addresses this challenge by developing an integrated pipeline that combines advanced 3D reconstruction with synthetic data generation. This approach allows us to create photorealistic 3D assets and generate diverse, realistic datasets, enabling better, faster, and safer AI model training.
By automating what once required months of manual work, our pipeline can transform how analysts, engineers, and researchers prepare data for intelligent detection systems. It reduces reliance on rare, inaccessible, or classified imagery and accelerates model development across defense, aerospace, and simulation domains. With our integrated workflow, analysts can build high-quality datasets all within controlled, reproducible environments. Our goal is to enable AI systems that can perform reliably in complex, high-stakes environments, even when real data is limited or unavailable.
First, for 3D reconstruction, we show how ordinary photos become precise simulation-ready 3D models. The 2D to 3D reconstruction process begins with neural radiance fields, or NERF, which learns how light behaves across a scene from a sparse set of those 2D images. This will allow us to synthesize new viewpoints and infer detailed geometry even when the original imagery is very limited. Traditional pipelines often require optimization per scene and can be very slow. To circumvent this issue, we enhance this with pre-trained models that use flow-guided diffusion transformers and structured latent representations. These advanced models generalize across scenes, producing cleaner reconstructions faster and with fewer restarts. For example here, we have several objects of interest that are shown reconstructing rapidly from the data that was input. After running the advanced model and producing a 3D object from the radiance field, we extract an initial mesh and move that into Blender to start our mesh optimization process. The first step in our mesh optimization process is to decimate the mesh in order to reduce the polygon count while also keeping the silhouette and any other high-frequency details intact. In the next step of optimization, we convert any triangles to quads, allowing for cleaner topology and easier editing. We then perform object extraction, retopology touch-ups, and surface cleanup, fixing any non-manifold edges and correcting normals. After converting to quads, extracting the object, and touching it up, we then validate the UVs to ensure textures hold up under close inspection and that any materials are shaded consistently. The final result of the process is a lightweight, accurate asset that loads quickly. It shades correctly and behaves predictably in downstream simulations. Here we can see one of our 3D models that has been rendered through this process and then optimized. In short, photos go in, NERF and diffusion models reconstruct dense, high-quality structures without that per-scene retraining, and then Blender refines topology, and the final meshes are clean, precise, and ready for deployment.
To generate our synthetic image data at scale within an integrated environment in which we can modify to support different scenarios, we have chosen to use the Digital Combat Simulator, or DCS, to create comprehensive synthetic datasets focused on military objects and vehicles. The visual fidelity and general realism of DCS make it an ideal testbed for generating synthetic image data to then train detection models on these image sets with the goal of enhancing and improving real-life dataset detection capabilities. Here, we can either import and use our own generated objects with methods previously covered, or we can utilize the simulator's numerous military 3D assets, many of which have limited real-world footage or imagery, but are represented very well within DCS. Through DCS, we can capture extensive visuals of rarely seen assets, such as Chinese, Russian, or other types of aircraft. DCS even has other naval and land-based vehicles available as well. DCS allows us to modify environmental conditions such as the time of day and weather. We have captured image data in noon and dusk lighting conditions, along with sunny, cloudy, rainy, and snowy weather scenarios. Along with an almost infinite range of possible camera angles and distances, DCS allows us to build a truly robust and varied image dataset. Given that images in the computer are created without natural camera artifacts, we utilize tools such as Reshade to apply image filters on our captured images to help simulate real-world camera response and image degradation. These filters approximate different camera and image looks, including analog CRT and VHS looks, to also account for lens distortion. This variability strengthens our trained AI models, making them more resilient and capable of performing under a wide range of operational conditions. We have created custom missions to support different scenarios, including generic and more basic taxi, takeoff, and low-flight cruise type missions. We've also created missions that demonstrate more challenging scenarios, including images where the main subjects experience occlusion from the camera and those where the objects are very far away from the camera, helping to test the limits of trained AI model recognition and detection. Each of these missions then receive the time of day, weather scenario, and image filters applied. For a single object, hundreds of thousands of images may be generated. One of the key benefits of synthetic data generation in our approach is that all of our scenario dataset capture techniques are repeatable and scalable. Our reconstruction methods for generating realistic 3D models, along with using tools such as the Digital Combat Simulator to help us generate vast quantities of synthetic image datasets, pave the way for integrating custom objects into future datasets, enhancing realism and mission-specific needs.
Now that we have curated our synthetic datasets, we are ready to begin the process of training AI object detection models. These models are designed to identify and classify objects of military interest across a wide range of operational conditions. Each detection is informed by thousands of labeled examples, enabling the model to distinguish subtle differences in size, shape, and orientation. This ensures reliable classification even when objects appear partially obscured or viewed from unconventional angles. The dataset that we use to train these models consists of large batches of synthetic images that capture variations in lighting, weather, and background, ensuring each model learns to generalize beyond ideal environments. We further augment the data to simulate real-world unpredictability. These transformations help the model build resilience, learning to detect targets whether they appear in fog, glare, or shadow. Our trained models now detect nearly 100 distinct object classes with high precision, performing robustly, even when faced with noise, motion blur, or cluttered backgrounds. This performance is a result of iterative tuning and validation across diverse scenarios. Whether tracking fast-moving aircraft or identifying camouflage vehicles, the models maintain consistent accuracy and low false positive rates. We measure performance using metrics like recall and mean average precision, or MAP, verifying that models remain reliable in both ideal and degraded scenes. These metrics provide a quantitative view of model behavior, helping us to pinpoint areas for improvement. A rising MAP curve signals accuracy and confidence in the model's ability to generalize across unseen data. Beyond basic detection, we've also developed specialized models, including aircraft payload identification and takeoff action recognition. The takeoff action recognition software is a dedicated aircraft pitch analysis tool designed for intelligence and engineering workflows. Analysts will be able to load either a single image or a batch of images. Then the software will automatically detect the aircraft and extract its centerline to estimate pitch relative to the horizon. The result is a robust, analyst-friendly system for rapidly producing validated, consistent pitch angle measurements from imagery. These capabilities allow analysts to extract technical insight from visual data. For example, identifying whether an aircraft is armed or observing its launch behavior can inform threat assessments and mission planning in real time. These advanced capabilities are essential for real-time decision making in defense intelligence workflows. As live feeds stream into command centers, AI overlays provide instant object recognition and classification. This accelerates situational awareness, allowing operators to respond faster and with greater precision, even under pressure. Each model is validated across challenging, high stakes scenarios to ensure consistent performance, even in unpredictable conditions. The goal is simple: build models that work in the lab, but also thrive in the field. Together, these results show how synthetic data accelerates AI readiness, building reliable, mission driven models for the real world. With robust detection and specialized capabilities, our models are ready to support defense operations at scale. Next, we'll explore how these systems are being applied and what's on the horizon for future developments.
This research pioneers a scalable pipeline that merges 3D reconstruction with synthetic data generation to revolutionize AI model training. By producing photorealistic, labeled datasets, our approach reduces data acquisition costs and accelerates model development for domains where real-world data is scarce, sensitive, or costly, such as defense and aerospace. Our pipeline has already enabled AI models to detect 30 to 50 object classes with high accuracy across diverse conditions. Its applications extend beyond defense, reaching into autonomous vehicles, robotics, and aerospace simulation, empowering AI to operate reliably in complex, real-world environments. Moving forward, we're enhancing dataset diversity by incorporating new object types and dynamic scenarios, such as real-time weather variation and multi-agent interactions. We're also advancing physically based rendering techniques to achieve near real-world fidelity, ensuring our AI models generalize more effectively to operational settings. Beyond technology, this work highlights how synthetic data can accelerate innovation safely, allowing AI to learn in environments that would be too costly, dangerous, or classified to access directly. Our mission is to empower the next generation of AI systems to adapt, learn, and operate responsibly in high-stakes, real-world missions. Thank you for watching. We're excited to push this technology even further, transforming how AI learns, innovates, and performs in the real world.